So good morning to you all. So in this class, we are going to talk about the design of surface drainage system. So, so the last class, so we were talking about all, the surface, both subsurface and as well as surface, drainage systems, components, and the layouts. So now in this class, we're going to focus on the design of surface drainage system. So in this, we'll be talking most of the things you learned in soil and water conservation, engineering. So there you might be knowing how to design grass waterways, so based on the required peak flow. So we are going, the similar kind of concept, we are going to use it here for surface drainage design. But subsurface will have, you know, the Hugout equation, other things. Okay, considering this, steady state and unsteady state flow conditions. But in this, we're focusing more on, two kinds of designs. So let's start here. The surface. Okay. She's not working. So it's a surface drainage design. So it's we all know what is the purpose of the surface drainage. So basically the surface drainage systems are used to remove the excess water from the farmland. That's the main purpose. So what are the excess water you expect? So excess water basically from rainfall and also from the adjacent area, if the particular area gets water, so that also could be excess, and also the irrigation. So these three ways the farm field can have this excess water. So in order to remove that excess water, there basically we are going to consider the two designs. So two designs. So that means if you have a farmland and you have the excess water, so how to dispose this water? Okay, so the first of all we should know what is the resulting runoff or peak runoff, right? Once there is a storm or you have an irrigation or whatever, so you have to estimate the runoff from the field. So knowing the runoff or expected runoff, so you are going to design a particular the channel. Okay, so that's why we have the two designs. The first design is we call the hydrologic design. Hydrologic design, and the second is hydraulic design. Right. So we will see one by one. So in case of hydrologic design, basically we are going to estimate the peak flow or peak runoff expected from the particular watershed or sub-watershed. And the second is hydraulic design. So knowing the peak flow, so you have to design a channel which can carry that peak flow. Okay, so these two things we'll be studying here. So let's focus on hydraulic design. Sorry, hydrologic design. The first thing is hydrologic design. Okay, so in case of hydrologic design, So you might be knowing the famous equations. One of them is a rational method. This is an empirical equation to find out rational method. So the empirical formula used to estimate the peak flow. Okay, this is commonly or most commonly used empirical relationship to estimate peak flow or peak runoff. So that is QP. Generally, we represent the peak flow rate as QP, and this is C into I into A. Okay, CIA. So where QP is the peak flow rate, that is meter cube per second, and so C is the runoff coefficient. So C is the runoff coefficient. So the C values are available in tables. So based on a particular the surface characteristics and soil type. Suppose you have sandy soil having the lot of grass cover on top. So for different things or different characteristics of the surface, you will have the runoff coefficient. So the runoff coefficient, in the sense, how much percentage of runoff can be expected from the land surface for a particular storm. Okay, so that's the runoff coefficient. It varies from 0 to 1, and I is the rainfall intensity. Rainfall intensity for a given return period. This is mm per hour. Okay, so be careful. It's not simple, rainfall intensity. Okay, so the rainfall intensity for a given return period. You all know what is return period, right? So the return period is the average number of years within which a given rainfall event will be expected to occur at least once. Suppose if I say 5 years return period, right? So the I is equal to, let's say 10 mm per hour. It's happening 5 years return periods. So that means it's not that the 10 mm 10 mm rainfall, 10 mm rainfall per hour will occur every 5 years. Okay, it's not that. So within this 5 years period, so this 10 mm per hour can occur anytime. Okay, so that's the meaning. Okay, and then A is equal to the area of the catchment. Area of the catchment. So that is in hectares. Okay, so if you put these values, I mean, if you make the units in hectares and all, you will have the formula. The formula would be so QP, which is equal to CIA divided by 360, where A is in hectares. If you put in hectares, I in mm per hour, and QP meter cube per second. C is a fraction. Okay, so it's a 360 is a 360 we are dividing because of we are converting the units and in order to bring meter cube per second. Okay, so there are some assumptions we need to consider while using this formula. The first thing is the rainfall which is happening, the intensity of rainfall should be uniform during that particular storm interval. So that is so assumptions assumptions are, suppose if you have, so this is the field surface, so the rainfall which is happening, so this should be uniform. It should have a uniform intensity for a duration at least equal to time of concentration. So uniform intensity for a duration at least equal to time of concentration. Let's define time of concentration with Tc. Okay, that's the time of concentration. So, and that is one thing. And the other thing is this, the rainfall intensity, this should be uniform throughout the, watershed or throughout the land surface, let's say. So everywhere, if you see, it should be uniform. So second, uniform across the watershed. So I should be uniform, across the watershed. So these two assumptions we have to, consider. Okay, so why we are doing this time of concentration? Anybody? So why the time of concentration we need to consider as the duration of storm? Anybody? So the question is, so during this, 5-year, 10-year, or 20-year return period, okay, the rainfall intensity, the value which is being used in rational method, why we should consider the time of concentration as the duration? Anyone? Okay. So, I mean, this is kind of a common sense, right? So, what we expect here, if you see the definition of time of concentration and also our, objective. So, our objective is to get the peak flow here. What is the peak flow? That's QP, right? So, when there is a rainfall which is happening on a land surface, we would expect, so initially, if you see the graph, so initially the runoff might be low from the beginning of the storm. Let's say T0, right? So then after that, the storm, the runoff will increase to a peak. Okay. So when do you get this peak? The peak, you will get the peak when the point, the runoff from the last point reaching to this point. Okay, so the travel time is time of concentration. So the time of concentration is the travel time of the remote, the water from the remote area, right, remote point to reach the watershed outlet. Okay, that is time of concentration. So then only you get the peak, right? So suppose if it is not reaching here, so that means the storm has stopped before the time of concentration. Okay, so then you don't get the peak. You don't get the peak, right? So maybe you will get somewhere here. Then after that it's going to fall. But this is expected peak. Okay, so suppose your storm is happening more than the time of concentration, duration happening more than time of concentration, you will get the peak. Then after that, it will be constant. Okay, after that, this will be constant. Then once the storm is stopped, then the runoff will be. Okay, So exactly, suppose when the duration is equal to time of concentration, you will get like this, because you will get the peak, and then the runoff will be reduced or decreasing. So this is more than time of concentration. The duration is more than time of concentration, and the duration is less than time of concentration. It will be like this. Okay, so this will be, this is not the actual peak, and this is the peak you expect from the particular watershed. Remember, this is completely depends on area to area and the characteristics. Okay, so that's why we need to get an intensity which is, which can satisfy this, at least satisfy this. Okay, that's why because for any structural design, so designing any structure, you need to see what is the maximum, flow can occur here. What is the maximum, the peak flow rate? It will be occur. So from this particular watershed, this is the maximum flow you can expect. So this we are taking it as a criteria, right? We are considering this QP as the design flow rate, and then we are going to, design the hydraulic design. Okay, this is the hydrologic design, and hydraulic design will have mostly the dimensions. Okay, finding out the dimensions. All right. Uh, so let's do some example. Here is a simple example. So this is example 1. A cultivated area of 40 hectares. So the area is given 40 hectares. Drains to a particular storm water inlet. The runoff coefficient for the drainage area has been estimated to be 0.4. So C is equal to 0.4. Based on a specified design return period and the time of concentration of the drainage area, the design storm intensity has been determined to be 10 mm per hour. So I is 10 mm per hour. So what is the peak runoff rate from this area to be used for design of stormwater inlet? Okay, so what is QP? So you can directly use this formula, that is QP is equal to CIA. So by 360 we are using, because the A is already given in hectares. Okay, so that is C is 0.4 and intensity 10 mm per hour, and area is 40 hectares divided by 360, and you get 0.44 meter cube per second. So having the runoff coefficient 0.4 and rainfall intensity 10 mm per hour. So what is the meaning of this rainfall intensity? So that means, so this much rainfall, that means 10 mm per hour might have happened, that the duration which will be equal to time of concentration. Okay, and so return period is hiding here, so it could be like 10 years or 5 years and all. So that is the intensity. So we expect, we expect maximum or the peak flow with this rainfall intensity. Okay, remember, so the rainfall intensity corresponding to the expected peak flow. Okay, that's a CIA. A is the area of the farmland, that's CIA 360. You get 0.44 meter cube per second. So this is design discharge, and you will be designing your waterway or trapezoidal channel or rectangular channel, which can carry this much, flow rate. Okay, and so as I mentioned, these values we can pick from some tables like C value, I value, right? So let's see how we can estimate these values if suppose there are some tables are given in the problem. Okay. Right. I'm going to reproduce the, the rational method, that procedure. Let's say the procedure. So first of all, area, right? So how do you find out the area of a land? So nowadays, advanced techniques are available using satellite images, or the maps, the government maps are available, or aerial photography. You can have, the survey maps. Aerial photographs. Okay. Or yeah, aerial photographs of that, or um, remote sensing. Okay, so this area you can get now, even the Google images from Google, you can also get the area in hectares. And the second parameter is runoff coefficient. Okay, that is C. So C is there are some tables available. So knowing the soil texture, topography, or vegetation, so you can get the C values. So generally, if the C value is 1 means, if C is equal to 1 means, so whatever, the rainfall which is happening, right? So let's say the P is the rainfall. So the same P will be resulted because there is no infiltration from the ground surface. The C is equal to 1. So that means 100% precipitation is being converted into rainfall. But whereas if C is equal to 0, that means nothing is coming out, so your runoff will be 0. So that means your precipitation, so the mostly it is going down, and your R is equal to P, here R equal to 0. Okay. So you have, so in between 1 and 0, so based on the soil type and the topography, so you will have the C values defined. There's a table available, so you can get from the table. So if you see here, yeah. So look at this. So this is the table, the value of runoff coefficient C for for different. Look at the soil texture for different soil textures, and also the topography and vegetation. For example, for pasture land or cultivated land, let's say the cultivated land for flat slope, the open sandy loam or clay loam, or this is the structure. So the C value expected will be 0.3 in this case. So the table will be given. So you have to pick the correct number and assign to C value here. Okay. And then similarly for rainfall intensity, I don't know whether I will be able to write down here. Let's put it done. Only I can write it here probably. Okay. So similarly for rainfall intensity. So for rainfall intensity, so you have first you have to find out the time of concentration, the TC. So you have to find out the time of concentration. So here, if you see, the time of concentration values are given from the table. So knowing the maximum length of flow, so that is watershed length, right? So the maximum length of flow and the catchment slope. So knowing the slope and knowing the maximum, length of slope, you can find out TC, right? That is time of concentration. Okay, so knowing the time of concentration, so you will find out the rainfall intensity by using, intensity duration curves. So that also, if you see here, so these are intensity duration curves. Okay, so you know the time of concentration, that's an x-axis, and knowing the return period, okay, and you can find out rainfall intensity. So these curves are prepared for different watersheds. It's already available, right? So you have to, knowing the particular area, you get this map and then find out time of concentration and the return period. So for different, structures, the return period will be different. So generally for field structures, 5 to 10 years. So for field structures, 5 to 10 years return period will be considered. For large farm dams, 50 years, gully control and small farm dams, 20 years. Okay, so based on a particular, structure, so you can, select the return period. So here the return periods are given. So suppose you are, designing it for a field structure, for example, these channels. So that is 5 to 10 years. So let's say that 10 years, this is the curve, that is duration and intensity curve. And your time of concentration is, let's say, 50 minutes. Okay. So then, so I'm hitting this curve at here and the corresponding, value will be my intensity. So that will be 60 mm per hour. Okay, so this way I will be calculated. So in order to find out I, so this is the procedure we need to follow. Go back to the notes. Yeah. Okay. So see, this is the runoff coefficient. And then third, as I mentioned, so one is runoff coefficient. The third is your intensity, rainfall intensity. So for rainfall intensity, what we did, first we found out the time of concentration. So from time of concentration, so knowing the return period, let me put it differently. Yeah. So first step is to find out time of concentration. So either you can use the table, or you can also use a formula that is a well-known formula, that is 0.0195 L power 0.77 and S power minus 0.385. Right? So 385, where TC is in minutes, the time of concentration. And if you don't have table, you'll have to use this formula. This is the maximum length of flow. That is in meters, and S is the watershed gradient. So S is the watershed gradient. Okay, that is meter per meter. That's a fraction. Okay, so knowing the TC value, so the next is you should have the what is the return period? You find out the return period for a particular right? Particular structure. Return period based on, sorry, for a form structure. So for form structure, 5 to 10 years, generally for form structures, generally it is 5 to 10 years. So since we are dealing with the form structures, so 5 to 10 years we have to use. So then the next is the flow duration curves. Okay, so you have time of concentration here and intensity here, and you have the curves. Okay, these are the let's say the return period curves. Okay, so knowing the time of concentration, just project it on return period, and the corresponding value on a y-axis will be the intensity. This is in mm per hour. So this way you can estimate. Okay, and then so now let's do an example here so you will understand better. So remember, so we are using the rational formula. So that is QP is equal CIA divided by 360. Okay, so this is in hectares and this is in mm per hour and this is in meter cube per second, and C is the runoff coefficient, that's in fraction. So we know how to find out C, how to find out I and A. So substituting this, you will know what is the QP expected from a particular area. Okay, let's see. So example, so a catchment of 15 hectares. So A is 15 hectares. A is composed of 5 hectares of permanent pasture. So this has two parts. One is 5 hectare and the other one is 10 hectare. Okay, so the two parts. So 5 hectare is a permanent pasture. Permanent pasture, and this is a soil group B. Whereas 10 hectares, this is a row crop. So this consists of a row crops. So 10 hectare land consists of row crops in poor condition, and this is a soil group C. So soil groups are like A, B, C, D. They are classified based on the drainage characteristics, right? So soil group C is a poor condition and D also very poor condition, and mostly the clay soils and all. Soil group A, B, so well-drained soils. So based on that, the soil groups, mostly the infiltration characteristics will come into picture. A total is 15 hectares. Out of that, 5 hectares permanent pasture, and then 10 hectares the row crops. So what peak flow is to be expected? The question is what QP expected from this 15 from a 1 in 5-year return period. So here return period is mentioned, and the maximum flow length which is 610 meter. This will be used to get the time of concentration, and the grade, watershed grade is equal to, grade means the gradient is equal to 2%. So you can either use this equation like TC equation, okay, 0.0195 L power 0.77, S power minus 0.385. So that equation can be used to find out. So the question here is to find out what is QP. So in order to find out QP, CIA 360. So area is given, and I you have to find out, right? So C you have to find out from the tables, and when you substitute it, you get the QP. Okay. So for TC, which is equal 0.19, 0.0195, 0.0195, L power 0.77, S power minus 0.385. So L is given, S is given. When you substitute it, so you get TC 12 minutes. You get 12 minutes, like 0.0195 into L is 610, right? 0.77 into S 2%, 0.02 into minus 3 minus 0.385. So you will get 12 minutes. And also you can use the TC values from the let's see this from here. This is a coefficient. Sorry. And the time of concentration, if you see this curve. So maximum length. So find out the maximum length that is in between 500 and 1000. So it's somewhere here. Okay. And 2% grade. So this is the 2% grade. So if you can do some kind of interpolation, so this will be, around 12 minutes you get. So it should be, it right now it is showing 11 and between 11 and 18. But once you do some interpolation, so you get 12 minutes from the table, or you can directly, estimate from the formula. And the second is, the rainfall intensity. So for rainfall intensity, we have the return period, and there is a table which is available. I'll just get that. Yeah. Oh, okay. That's not there here. Yeah. So this is the TC in 12 minutes you get. This is the TC 12 minute, and there is a the rainfall intensity duration, the corresponding to the return period, and the maximum intensity. Okay, so that, I mean, if you use the duration curves, for example, you have TC here, and this is I for a particular return period. So you get the rainfall intensity. Okay, so we're going to supply that. We're going to supply this curve, and you can identify easily for knowing the return period and the intensity. So in this case, using the flow duration curve, right? So rainfall intensity, you get 73 mm per hour. So using the flow duration curve. Okay. So now I is known. So the next is the coefficient, so the C value. So for C, for different soil groups, right? So if you see for different soil groups, like this, if you see it here, okay. In our case, we have two, lands, the areas. One is 5 hectares, the other one is 10 hectares. Okay. So one is soil group B and the other one is soil group C. So for soil group B, so here if you see the soil group, okay, for soil group B, and then we have a row crop, not a pasture land. This is the pasture land and soil group B. And so what is the cover condition? Coefficient C. So the intensity what we get here is, so in our case, it is 12 minutes, right? So it should be like, 25. No, it is 73 mm per hour, right? So in our case, the intensity I is equal 73 mm per hour. So here the intensities are given. So 73 would be between 25 and 100. Okay. So the pasture land corresponding to, it will be somewhere here, right? This is the pasture in good condition, so that you will have somewhere like 0.17, right? So, uh, but you should have the, what you call, the interpolation. So using the interpolation technique, because this is not exact, this is corresponding to the 100. So you will, 73 mm means it's in between, close to 100, right? So your value should be between 0.02 to 0.17. So after interpolation, so you get the C value here for this 0.17, 0.14. So 0.14 for here C value. So similarly for soil group C, so we have a row crop and the intensities between 25 and 100. Okay, for row crops, so you get in between, 0.69 and 0.71. Okay, so after interpolation, again, let's say this is C1 and C2. After interpolation, you get 0.71. Right. So this way you need to find out the, this way you need to find out, the C1 and C2 for corresponding to 5 hectare land versus 10 hectare land. And you are going to, find out the average C value. So that average C would be, go back to notes. I'm sorry. Yeah. So the C value, what we observed, but what we estimated. So one for soil group B, for soil group B, 5 hectares, right? C1 is equal to 0.14. Similarly, for soil group C, this is 10 hectares. C2 is equal to 0.71. So the average C, which is equal to C1 into, let's say, the area A1 plus C2 into A2 divided by A1 plus A2. So this is the weighted average. If you can use the weighted average, so you get C value as 0.52. Okay, C value. Yeah. So how do you get this? This you get like, points 14 into 5 hectare plus 0.71 into 10 hectare divided by 15 hectares. You get that. So now we know C value, I value, and A value. So now we substitute this equation. So A is equal to 15 hectares and C is equal to 0.52 and I is equal to 73 mm per hour. Okay, substituting this, QP is equal to CIA by 360, so that is 0.52 into 73 into 15 divided by 360, so you get 1.6 meter cube per second. So this is the peak flow rate you can expect from the entire 15 hectares, which contains 5 hectares of pasture and 10 hectares of row crops, agricultural land. Okay, so and then the next method in finding out the QP is SCS curve number method. So the second method to find the QP so that is SCS curve number method. Right? SCS curve number method. So this is Soil Conservation Service curve number method. So this method is basically the relations from the relationship between rainfall amount and direct runoff. Okay, this is basically from rainfall versus runoff, direct runoff. So this from this relationship you can this is based on this what is the relationship between rainfall and runoff. So based on that, this is formulated. So these relations are defined by a series of curvilinear graphs, which are called curves. Okay, so the curve represents the relation between rainfall and runoff for a set of hydrological conditions. So generally, the equation used to find out the Q, which is the discharge, will be equal to P minus 0.2 S whole square divided by P plus 0.85 into S. So where S is basically the potential storage. So any soil group or any soil with a certain characteristics, how much amount of water it can hold, so that the area can result a particular runoff volume. Okay, that is S. This is the storage. It represents the potential storage. So the Q is the direct runoff depth. Those all in depth units. So Q is direct runoff depth. This is in mm. And P is the storm rainfall. This is also mm. And S is the maximum potential difference between rainfall and runoff. This is also in mm. Okay, so starting at the time that storm begins. Okay, so then we're going to, so US SCS um, is given, he has given relationship between the potential difference, the storage like S versus curve number. Okay, so for example, S is defined or estimated with 25400 divided by curve number minus 254. Okay, so the curve number generally varies from 0 to 100. Okay, 100 assumes the total runoff from the rainfall, and therefore S is equal to 0 and P is equal to Q. So when Cn is equal to 100, so that means the complete, the storage is 0, and whatever the precipitation happening, so that is completely going as runoff. So P is equal to Q. So you can substitute Cn is equal to 100. So you get S is equal to 0. So when you substitute S equal to 0 in the above equation, so you get P is equal to Q. Okay, you put this in S equal to 0 here, Q is equal to P. Okay. I mean, if you substitute it here, Q is equal to P minus 0.2 S whole square divided by P plus 0.85 S. Right, since S equal to 0 here, so P square by P, which is equal to P. So the Q is equal to P. So that means for Cn is equal to 100, from the above equation, if you see, if you put 100 here, if you put 100 here, 254 divided by 100, 254, so you get S equal to 0. And then when you when you substitute S equal to 0 in the equation 1, let's say, and you get P square by P, which is equal to P. So curve number 100 represents, it's a perfect, I mean, the soil is, very well compacted, the infiltration is 0. So there is no storage. So whatever precipitation is happening, that is running off. Okay. All right. So for the curve number, hydrologic design, for curve numbers, the soils and catchment condition, antecedent moisture content, moisture condition. So you have different, tables available. For example, if you see, so these curve number values are obtained from the tables. Cn values are obtained from tables. So based on the soil and catchment condition. So for example, if you see, so in this table, if you observe, see the soil groups here. So this is for soil group C, right? Or soil group D, soil group B, soil group A. So based on this particular soil group, and then land use like fallow row, small grains, close, pasture land, and all. So the treatment is like a different, the crop treatment like straight row, contoured, whether the area has been contoured or not, or I mean the crops are, row crops or not. So all those things based on the treatment and condition, the drainage condition, where it's a poor drainage, good drainage, or so based on that, and soil groups, you can select a particular Cn value. Okay, so any Cn value. So Cn will be obtained from the table. So soil group A, it's basically well-drained sand or gravel or high infiltration rate. Whereas soil group B is moderately well-drained soil and moderate infiltration rate with fine to moderate coarse texture. Soil group C is slow infiltration rate, moderate to fine texture, and soil group D is very slow infiltration and mainly clay material relatively impervious. So in the earlier example, if you see Cn is equal to 100, that means so that is falling into soil group D. So you can also see from the values they are close to the soil group D, they're close to 100. So that means there will be a lot of runoff you expect from this soil group. Okay. And then if you see this curve number, I mean, you can also get these values from the particular from the curves, right? So one is the rainfall, that is P, the precipitation in inches, and direct rain runoff for Q. Okay, so these the graphs are available for different watersheds. So the curves you're seeing here, these are all curve numbers like CN 100 and varies from 40 to 100. These are curve numbers. So knowing the particular rainfall, let's say 8 inches, and I know the curve number 40, right? Rainfall 8 inches 40, and the corresponding direct runoff, we can get it from this, the graph. So these graphs are available for some of the watersheds. We can directly adopt from these, adopt the direct runoff, estimate the direct runoff from the graphs. So in this, the first thing we should know is curve number. So knowing the curve number for a particular area and knowing the rainfall, so what is the corresponding direct runoff? Okay, so these table, either you can use table or so both table as well as the combination of table and graph should be used. So from the table, you know the curve number, and from the graph, you know the direct runoff for a particular thing. Okay. All right. So this is a curve number method, SES curve number. So I'll give you a break for 5 minutes, and then we'll join again for an example. Okay, welcome back. So in this example 2, in a 350 hectare watershed, the curve number value was assumed as 70 for antecedent moisture content 3. Okay, this is the group based on the soil group based on antecedent moisture content. So the question here is to estimate the value of direct runoff volume for the following 4 days of rainfall. The AMC or the antecedent moisture content on July 1st was of category 3. Use standard SCS curve number equation. Okay, and to find out that. And B, what would be the runoff if the curve number for category 3 is 80? Okay, so the storm values given. So you find out the direct runoff expected from this particular storm. Okay, and suppose if the curve number is 80, what would be the direct runoff? This is the the question. So let's see what is the question for A. Let's see what are the given values. So we know Cn category 3, which is equal to 70. Okay, so that is already given. And then S is equal to, we have to use the equation 25400 divided by curve number minus 254. And if you substitute curve number here, that is 254 0007 divided by 70 minus 254, so which will be 108.86. so this is the potential storage you expect from this particular area. Okay, so now let's find out Q value. That is Q is equal to P minus 0.2 S whole square divided by P plus 0.8 S. So substitute S value, that is P minus 0.2 into 108.66 whole square divided by P plus 0.8 into 108.66. So when you substitute these values, you get direct runoff. That is P minus 21.78 whole square divided by P plus 87.09. Okay, so this is the Q value you get, right? So the Q, so that means this equation will tell you, so when this P value, if P is greater than 21.78 mm, so then only you will get the direct runoff. Okay, so this, from this equation it is clear that, so when P is greater than 21 point, so that means if you substitute 21.78 here exactly, so you get Q is equal to 0, and also it should be more than 21.78. remember this, it should be more than 21.78. from the equation it is clear that, so is P minus 21.78. So P should be more than 21.78 in order to get the direct runoff. Otherwise, it will get 0. So if it is less, you have to consider it as a 0. Okay. Now we'll bring the table, that is the date we have, and then the P, we already know the storm on each day. I mean the precipitation on each day, and the Q mm. Right. So So date July 1, for July 1 or July 1st, the precipitation is 50. And now we use the equation, substitute p-value 50, and you get 5.81 from this equation. Okay, when you substitute p-value. All right. And then the next is for July 2nd. For July 2nd, the p-value is 20. So since it is less than 21.78, you can put, the direct runoff as 0, because this is less than 21.78. Maybe I should write it not here. I should write it here. If it is less than 21.78, so that's why you get 0 here. Now July 3, the precipitation is 30. So since it is more than 21.78, so there is a direct runoff 0.58 mm. And 4th, so for July 4th, so let's say this is given 18. So since it is less than 21.78, you will get a 0. This is less than 21.78. The direct runoff will be 0. Right. So now let's see the total. So the total precipitation is during these 4 days 118 mm, and 6.39 mm is your direct runoff. Okay. So from here, the total volume, that means runoff volume of water run off from the catchment so let's say the VR, which is equal to, so you have to find out, I mean the area is given, you see in the equation, that is 350 hectares, so that is 10 power 4 into 6.39 mm, so convert into meters, so divided by 1000, so the 22365 meter cube of runoff water is being generated from the area. Okay, so next question number B, like question B. So suppose if there is a curve number, category 3 is equal to 80. Okay, the earlier calculation was for 70. Now it's if it is 80. So you repeat the same, procedure. So find out S value, that is 25400 divided by 80 minus 254. So 80 is the curve number. So you'll get 63.5 is the maximum potential storage. So now direct runoff will be P minus 0.2 S whole square divided by P plus 0.8 S. When you substitute it here, so P minus 0.2 into 63.5 whole square, that is S value substituted, divided by P plus 0.8 into 63.5. Okay, so now Q value, you get P minus 12.7 whole square divided by P plus 50.8. Okay, so runoff will be generated when P value greater than, or precipitation is greater than 12.7. Okay, this is the for P greater than 12.7 mm. Okay, so we'll do the same, repeat the same steps same table for different days. So let's say the date, and P is in mm, and you get Q, this is in mm. Let's say this is July 1, precipitation 50, so this is greater than 12.7, you get 13.8, and for July 2, so 20, and use this equation and find out this is a 0.75, and this is July 3, 30, and when you use that equation you get 3.7, July 4th, 18, and this is 0.41. Now the total, this is same 118, and now 18.66 mm is the direct runoff. You can clearly see when you change the curve number from 70 to 80, the runoff or the depth of runoff got increased. Okay, so that will tell you, like, when you're moving towards 100, you get more runoff. Okay, so find out the runoff volume. So runoff volume, that is VR, which is equal 350 hectares, 10 power 4 meter cube, sorry, meter square, into 18.66. Since it is in mm, you convert that into meters by dividing with 1000, and you get 65310 meter cube. Okay, so VR for curve number 70, and this is VR for curve number 80. So when curve number increases, your runoff rate will increase. Okay, so this is all about the finding out the runoff or peak runoff expected from a watershed. Okay, so the next is, so that's all about the hydrologic design, right? So in case of hydrologic design, our aim is to find out the peak flow rate expected from a known area with known the characteristics. Okay, so now second step. The first step is hydrologic design. The second step is hydraulic design. So hydrologic design, you expect, you estimate QP, that's the maximum runoff, expected from the land area. In the second case, you are going to find out the dimensions of the field drainage or open ditch. Okay. Yeah. So this is hydraulic design. So this basically refers to the geometrical elements of the drainage channel to carry the design runoff. So to carry the QP. Okay. So the geometrical elements of a channel, which includes, so this is basically geometrical elements of a channel. So this is what we are going to determine. So this basically has the bottom width and then the depth. Okay. So other essential information, so that will be in order to find out, you should have like a stable side slopes, bed slope, and roughness parameter. So generally the Mannix roughness coefficient we need to consider. Okay. So the channel should be designed to fulfill the following criteria. It should carry. So what is the criteria? The design criteria. So channel design criteria. So this should carry the design discharge. First of all, should carry design discharge. This is number one. And number two should be stable. Should have stable slope. It should not be collapsed. And also the longitudinal side slopes. Right? So longitudinal side slopes are important because that will help in avoiding scouring, silting, and all other things. Okay. So the next is, so the first thing we know the QP value you have to, in order to design the QP should be estimated. That we just learned how to estimate QP for a particular area. And then the next is the second, so the steps, if you see in designing the channel. So number one is determine QP. So that is already we did. And second is, so QP using either rational method or second SCS curve number method. So any method you can use based on the given data. And second is the grade. So the grade is important. It should have a maximum possible value without exceeding the permissible velocity. Right. So if it exceeds the permissible velocity, so that's going to cause, or that's going to erode, the channel. So make sure that the grade should be in such a way that it should have maximum possible value without exceeding the permissible velocity. And the grade should not be so low as to allow silting and should be as uniform as possible. So it should not be more or should not be low. So for that, there is a table available. So from the table, you will know what is the maximum permissible velocity. So for non-vegetated canals or non-vegetated channels for different soil conditions. Okay, so the table will comprise different values of the grades, possible grades, or the safe grade values for different, the vegetation condition. So let's see what are those values. Maybe I got a table. Okay, maybe. Yeah. All right. So the table, right now I'm going to describe that. I'll provide these tables anyway for your reference. You can go through the tables. I'm sorry. Okay, so basically the table contains the, in first column you have the canal material or the channel material. Let's say the channel material. So channel material in the sense, what is the type of the soil the land has. Okay, so sandy loam, fine sand, silt loam, alluvial silt, ordinary firm loam, So all these things. Okay. And then the corresponding, the column number 2, you have a Mannix N. This is the roughness coefficient corresponding to the material. And then the velocity. Okay. So these permissible velocities are given. So if based on the type of the water you have. Okay. So water. So water could be clear water. If it is a clear water, or the water is little the colloids like suspended sediments, or the water has sand particles, sand or gravel, sand or gravel particles. So based on the particular type of water you expect, so the maximum permissible velocities are given here and the corresponding Mannix N. So for example here, fine sand. So the Mannix N will be 0.02. And if you are expecting clear water, the velocity, the permissible velocity, 0.45 meter per second. If it is, if the water contains the colloids, it will be 0.75 meter per second. If it contains the sand or gravel, the water contains the sand, gravel fragments, this will be 0.45 meter per second. So this is the permissible velocities. The table is available. So based on that, so Mannix N is known, velocity is known, and then so from these two values, a particular material, you can use Mannix formula to find out, the grain. Okay, that is S. So what is the Mannix formula? That is V is equal to 1 by N S power 2 by 3. Sorry, R power 2 by 3 S power half. So this is the Mannix formula. So V and N values known from this soil material, and R is the geometric parameter in a way. So that is hydraulic radius, and S you can find out. Okay, so this is mostly for trapezoidal channels we consider because of the stability into consideration. So assuming the side slopes and all R can be estimated. Okay. So velocity, this is in meter per second, and this is the maximum permissible velocity. N is the Mannix roughness coefficient. So R is the hydraulic radius. S is the bottom slope. Okay, so this way you can find out the cross-sectional view, right? So generally the cross-section, what we consider for the channel will be the trapezoidal. Okay, and this got a side slope that is Z and 1. This is the side slope, and this is the bottom width. This is a B, let's say B. and this is the freeboard. So freeboard is being provided in order to compensate if there is any silting or not. And then you have theta here. So this is the channel slope, I mean the angle between the bottom with the channel, I mean side. And this is the D. This is the depth of the channel. And this is the maximum depth, capital D, is the total depth, you can say. Okay. And this is the top width after considering the freeboard. Okay. So D is the design depth, capital D is the total depth, theta is the angle of side slope, okay. So again, so you also need to maintain about 3 meters of berm. So in order to avoid any collapsing, as well as you also should have the walk area. This is a walk area, as well as if suppose if you have a burn immediately after the slope, so there is a chance of collapsing and all soil falling into the channel. So you should maintain a berm. We call it berm, DRM. So berm should have a width of 3 meters. Okay. So all these things, this is the cross-sectional view. So this is the cross-sectional view of the trapezoidal, channel. Now we like to see how we can estimate the, the dimensions, but mostly the breadth and width. Okay. So we also have this, table for defining the side slopes. So there is a table for, there is a table for side slopes. So this is also, you have a soil type on column 1 and the side slopes. Okay, the side slopes are for shallow channels, deep channels. So you have shallow ditches versus deep ditches, deep channels. So slopes available. So based on the soil type, for example, you have a sandy loam. So sandy loam soils, you have 1.5:1 if you're planning for shallow. Okay, or 2:1 you have to maintain. So 2 horizontal and 1 vertical. Similarly, 1.5 horizontal, 1 vertical. So that means if D is the depth, so 1.5D is your horizontal component. So similarly, this is D is to 2D, so the double. Okay. So this is for on sandy loam, and similarly you'll have the side slopes for loose sand and clay and silty loam, stiff clay, peat and muck. So for all these soil material, you'll have the side slopes already given in the table. Okay. So with this information, the table number 1, so what we got was the permissible velocity and Mannix N. Okay. and then this particular soil type. So knowing the particular soil type, so you will find out the permissible velocity, Mannix N, as well as the side slopes. Okay, so from these two tables. So with this information and also the estimated, QP, so you will be finding out the, the dimensions of the particular channel. Okay, so for example, here, so determine, let's say I'm going to read out. Yeah, determine the efficient trapezoidal section of a drainage ditch required to carry a peak runoff of 1.4 meter cube per second. The channel is constructed in alluvial silts. The bed slope may be assumed 1 by 3000 approximately as per existing topographical condition. So this is the question. So in this question, it is given that QP, so there is a QP of 1.4 meter cube per second. So it's already given. If this is not given, you need to estimate using, the procedure we explained in the previous class. 1.4 meter cube per second. And then the channel type, what is the trapezoidal channel? Trapezoidal channel. This is one thing. And then the soil type is alluvial silt. So bed slope is given. So S is equal to 1 by 3000. Okay. So this much information is given. So QP is given, the total direct runoff to be disposed of, and you need to design the trapezoidal channel for an alluvial silt, which with a grade of 1 by 3000. Okay. So let's see how to design this. For this case, since QP is given, so you have to find out what is velocity. So that is Q is equal to A into V. You know this formula, right? So continuity equation, if you see Q is equal to A into V, so V is equal to 1 by N R power 2 by 3 S power 1 by 2. Okay, so substitute it in here, you get Q is equal to A into 1 by N R power 2 by 3 S power half, or A R power 2 by 3. So you put take these two terms and the rest you separate it out. So Q into N divided by square root of S. Okay. So now, so from table 1, so I'm going to take the table values from the table where you have the particular soil type and the corresponding N values. So from table get N value for the soil type for the given okay. So that is N is equal to 0.020. So this is what we get from table. I already explained. For a particular soil, you will get the N value and the corresponding V value also you get. So now substitute N value here. Now A R power 2 by 3, which is equal to Q is given 1.4 and you obtained just now 0.02 divided by square root of 1 by 3000, which is equal to 1.5336. So this is A R power 2 by 3. Okay. So again, from table 2, I just explained for the side slopes. For trapezoidal channel, and also for the particular, the soil type. For the soil type, so slide slope of 1.5:1 is recommended from the table. Okay. So now, suppose you have a trapezoidal channel with side slopes of 1.5:1. So that means this is B and this is D. So this portion will be 1.5D. Okay, this horizontal portion will be 1.5D. So this is D, and this will be 1.5D based on the side slopes. Okay, so now, so what would be the top width? Okay, so let's say the top width will be B plus 1.5 D plus 1.5 D. So that means here also you get 1.5 D, and this is B, right, based on the geometry. So the top width will be B plus 1.5 D plus 1.5 D. So that is B plus 3D. So this is the top width. Now wetted perimeter. So why we are doing all this? Because of the wetted perimeter, AR power 2 by 3. If you see AR power 2 by 3, so in order to get R value, so we need, so R is equal to A by P, right? So A is the area of cross section and P is the perimeter. So in order to get, so that's why the wetted perimeter we get here, and area of cross section, then you get R and you substitute it back and you get the, the dimensions. So that is the idea here. So the wetted perimeter, that is, let's say the P. So which will be B plus, 2 into square root of D square plus 1.5D whole square. Okay, how do you get? So the wetted perimeter will be this, right? From this point to this point to this point. This is the wetted perimeter. So in order to get, so this length is known, that is B. Okay. And now how to get this length? This length is, if you see this is the triangle portion, right? This is a triangle. So knowing this value and this value, you can find out this value, that is D square plus 1.5 D square. Since there's a two lengths, this is another length, you have to multiply with the 2 and you get now B. So now you get B plus 2 into square root of 3.25 D square. Okay, or this is B plus 3.606 D. This is your P, perimeter. Okay, now find out A, capital A, which is equal to area of cross section. You know the trapezoidal area of cross section. Okay, so you have to find out what is the sum of the parallel sides, right? Bottom and top width multiplied by the depth divided by 2. So that will be like a B plus, so B is the one parallel, the bottom, you can see, and at the top will be B plus 3D, that's the top width. You can see this is the top width. So one bottom and top, and multiplied by D by 2. Okay. So this will be like a B plus 1.5 D into D. Okay. So this is area. So as I mentioned, in order to find out R, hydraulic radius, so that is R equal to A by P. So A would be plus 1.5 into D divided by P. So P is B plus 3.606 D. That is R value. Okay. Now A R power 2 by 3, which is equal to, it's already there. We have that value. A R power 2 by 3 value is here. You see it here. So this is A R power 2 by 3 value. So we are going to equate this A R power 2 by 3, okay, with this equation. So A R power 2 by 3 will be 1.4 into 0.020 divided by square root of 1 by 3000, and we have that value 1.5336. Okay, that's already there, 1.5336. So now we are going to equate AR power 2 by 3 with this value. So that will be B, A value B plus 1.5 into D. This is A, multiplied by R values B plus 1.5 D into D divided by B plus 3.606 into D. Into 2 by 3, which is equal to 1.5336. So this represents A, where this represents R. Okay, A R power 2 by 3 is equal to the value we got here. This one, this is here. Now, after simplification, so and before that, so we have to find out the efficient section. So to find out the efficient, section, efficient cross section of trapezoidal channel. So I'm not going to derive, but the rule is, right, for efficient, B is equal to 2D tan theta by 2. So this is for efficient cross section. So there is a derivation. How to find out this efficient cross section? What is the relation between B and D? Okay, and if you have theta, the channel slope, slope. So we are going to use this equation for finding out the efficient cross section. So only thing here, we have to find what is theta. Okay, so that means for 1.5:1, this side slopes, so tan theta will be 0.667, because if you see this channel slope, right? This is the channel slope. Let's say this is a theta, and and this is 1.5. As I said, this is 1.5, and this is 1. Okay, and if you have the same thing here, so this will be 1, and this will be 1.5, and tan theta will be 1 by 1.5. Tan theta, so this basically obtained as tan theta is equal to 1 by 1.5, so that will be 0.667, and now theta is equal to tan inverse, 0.667, so that will be 33.69 degree. So that is theta. If you can maintain 33.69 degree, and the corresponding tan theta by 2 will be 0.3038, and for efficient cross section, B is equal to 2d tan theta by 2, so that is equal to 2d into 0.3028, which should be equal to 0.6055d. So B and D have the relationship like this, in order to have efficient cross section. So now we're going to substitute it here back into that ART. So we have that A R power 2 by 3, right? So we are going to substitute it here. That is B plus 1.5D into D into B plus 1.5D divided into D divided by B plus 3.606D 2 by 3, which is equal to 1.5336. Okay, so now I'm going to substitute D, like substitute for B. So now if I do, I get like 2.1055 D square and 2.1055 D D square divided by 4.2116D 2 by 3, which is equal to 1.5336. And when I simplify, I get D is equal to 1.091 meters. And if I substitute it back into efficient cross section, the relationships, I get B is equal to 0.6055. Okay, or which is equal to this is meters, so this will be equal to 61 centimeter. Okay, so you can also cross check with the permissible velocity. Okay, if you want to cross check with permissible velocity, so you have R is equal to A by P. This is hydraulic radius. If you substitute these values, these B and D values, what you obtain, that is 0.66 plus 1.5 into 1.091 into again 1.091 divided by 0.66 plus 3.606 into 1.091, and you get 0.5449 meter, and substitute this R value into velocity equation, that is V is equal to 1 by N R power 2 by 3 S per half. You get 1.02, 0.5449 power 2 by 3 into 1 by 3000 1 by 2, and you get 0.609 meter per second. Okay, and this one is less than 1.0 meter per second from the table. This is from the table. Sorry. So this is from the table. So with this particular soil, the permissible velocity is less than 1.05 meter per second, but you get